Thank you for coming to the data training webinar, Path 202, Longitudinal Data Analysis Approaches with PATH Study Data, Part 2. This webinar will be led by Westat statisticians, Dr. Jean Opsommer and Dr. Xiaoshu Zhu. Disclaimer: this is not a formal dissemination of information, and the views and opinions expressed in this presentation are those of the authors only and do not necessarily represent the views, official policy, or position of the U.S. Department of Health and Human Services or any of its affiliated institutions or agencies. The link to a transcript that includes descriptions of all complex images and information is available in the YouTube video description. Just a quick recap: this is the outline for the first part of the webinar. We talked about 3 examples for linear regression, linear mixed model, and generalized estimating equation model. And a reminder that the examples provided in both Part 1 and Part 2 of this webinar are to aid researchers in their analysis of PATH study data, but do not represent an endorsement of any particular analytic method. For official PATH study estimates, see the PATH study data tables and figures on the ICPSR website. In the second part, we will start with an example very similar to the last example in Part 1. But this time, we will allow the respondents who respond in at least one of the 3 waves in the analysis using the single wave weights. We will discuss why we would do that and how we should do this type of analysis and interpret results. Then we will cover a latent class analysis example that will use a different software called M-plus. In this example, we will try to fit things that are latent rather than just having a set of explicit variables. In the last section, we will wrap things up and share a few more things that we want to leave you with. So let's look at the first example with stacks of multiple sets of weights. Some analysts may be interested in combining datasets with single wave weights instead of using the all waves weights. Say you're interested in waves 1, 2, and 3 and use all waves weights. That means you are only going to have people who responded in every wave. Anybody who doesn't answer all 3 waves will be dropped. But if you're using single wave weights, then for example, you don't have to drop those people because people who participated in waves 1 and 2 but not 3 do have a single wave weight. It's attractive to be able to use people who might not have participated every time but have at least one interview. Turns out that you can do that using methods that are very similar to what we've done already, and it does give you a bigger sample size. You may wonder whether there are any other advantages of doing this. The truth is, the bigger sample size is the only advantage. You might think, not unreasonably, that if you have a bigger sample size, you are going to get more significant results. Therefore, it's always a good thing to do. One of the things we are going to show you here is that that's not necessarily the case either. So let's look at our example. This is the same generalized estimating equation model example we reviewed in Part 1. It's a logistic regression model, but the same respondents can appear multiple times. Again, the question we are going to look at is current smokeless tobacco use associated with poorer physical health after controlling for demographic characteristics? The physical health outcome is self-reported in the interview, and we recode it into 2 categories: good and not good health. We would like to answer this question using multiple waves of data. In Part 1, we used the all waves weights to do this. So every respondent in our dataset would have data for waves 1, 2, and 3. Here we are using anybody who has data at any waves. That means we will be using single wave weights, and we'll see what changes compared to the all waves approach. Here you have 76,000 observations if you use the wave 3 all waves weights. The mean of the all wave weights is about 9,300, meaning every person in there represents on average 9,300 people in the population. We will come back to talk about the population as well. But if you are stacking single wave weights, then instead of 76,000 observations, you have 83,000. The sample size is definitely increased. Although you are increasing the sample size, you are in fact representing the same population. The mean weight is lower. Now everyone represents about, on average, 8,400 people in the population. Before we go into the analysis, let's think a little bit about the weights in those datasets and the typical interpretation of weights. It's easiest to look at the all-wave weights version. This weight is given to every person who was observed 3 times because we are combining 3 waves. This person represents W individuals in the population. W is its weight. So if you have a given person and the weight for that person is 10,000, then conceptually there are 10,000 people in the US population that this person represents. If you take all those individuals who are in the dataset and sum up all their weights, you basically end up with the size of the US population, which is the simplest explanation. Of course, if you're looking at specific characteristics, like the people who smoke frequently in a given wave, and you sum up all their weights, then that's an estimate of all the people in the US who have that particular behavior at that wave. But now, when you're looking at this dataset, that is not just a single snapshot of the US population, but is in fact 3 different snapshots. Because every one of those people who represents the US population was observed at wave 1, wave 2, and wave 3. If you sum up the weights, it's really 3 times the US population. The population by year is what you're observing. So you are actually observing the US population in year 1, year 2, and year 3. This is obvious with the all waves weights. What's interesting about this is the same interpretation also holds when you are combining single wave weights. When you take one of those waves, the sum of the weights in that wave will represent the US population. In the next wave, it's a different set of individuals because some of them didn't appear in the previous wave, etc. The total number of individual changes. But in the second wave, those people represent the whole US population in that wave. This is true for every single wave. If you sum over all the individuals in a wave, you get the US population. If you sum over all the observations in your dataset, it still represents the same total 3 times the US population, but they're potentially different people in those waves. The main thing here is that thinking about what those weights mean, regardless of whether you have a full dataset where every person appears every wave, or the one that you put together yourself by combining single-wave datasets, the interpretation stays the same.
This is a diagram that presumably you are already familiar with from the previous example. And the main change here from the previous example is that now, instead of having a single set of weights that you append to your dataset, we have multiple sets of weights that are attached to every one of those wave-specific datasets. And each of them comes with its own replicate weights. It's still a matter of stacking all those various datasets together. Regardless of whether a person appears one time or multiple times, they inherit their wave-specific weight and the specific replicate weights from that wave. When you do this, you go through the same procedure we've been describing, which means you fit the point estimates first, then you use the macro to fit the 100 replicates. Then you also use the macro to compute the estimated variances and standard errors. Here are the results. These are the point estimates for the parameters, their standard errors, and significance levels. We also have the correlation parameter because we still fit the repeated measurement model, accounting for the fact that some people can appear once, twice, or 3 times. Unlike the all waves approach, when they all appear 3 times here. Here they appear a different number of times, but you can still fit the same model with the same correlation structure. For comparison, on the right are the same analysis on the dataset that uses the all waves weights. Recall that in that dataset, every person appears 3 times. Looking at the correlation, they are not the same because it's a different dataset, but they are pretty similar. Looking at the point estimates, they have the same sign and roughly the same magnitude. But if you look at the p-values, they are quite different in certain places. For example, if you look at the coefficient for sex, you see that in the model where you are using the single wave weights or the bigger dataset, that variable is not significant. While if you fit the same model with all waves weight, which is a little smaller, it's significant with p-value equals 0.01. The coefficient of smokeless tobacco is significant in both models. But you can see that the p-value in the single wave weight model is much larger than that in the all waves weight model. In the race ethnicity variable, one level's p-value changes in the two models, but both of them are not significant. The question is then, why is this happening even though my dataset is quite a bit bigger? When I combine single wave datasets, my significance might switch from being significant to non-significant, and vice versa. When you are stacking the dataset, your sample size increases. What typically happens, with very few exceptions, is your stand errors are going to be smaller because you have a larger sample. However, you don't have any control over the estimates of coefficients. They are going to be similar, but they might be bigger or smaller, more negative or positive. They will move around because those changes are random. Therefore, even though you get smaller stand errors, your coefficient could go in either direction. You don't know why you are always going to get more significant results with more sample. That's something good to keep in mind. If we go back to the previous slide, you can see in the stand error column what I just mentioned holds, meaning all those stand errors from the larger dataset are smaller than the stand errors from the smaller dataset. Let's look at the estimates for sex. The point estimate is 0.057 in the bigger set. It used to be 0.111 in the smaller set. So the change basically doubled. You will need more to offset the decrease in stand error. As a result, in the single wave model, the stand error is smaller, but the coefficient is not significant. Whereas in the stand error in the all waves weight is bigger, but is significant. This is intended to be a cautionary tale when you are doing this type of analysis. Here is a general recommendation on this. If you combine single wave versions of data and the associated weights, those are valid. But you have to be careful, especially if you are trying to look for patterns that hold across waves. However, our current example didn't look at this. We select this example to look at things that are only within a wave. Is good health in a wave associated with smoking behavior in that wave? If you are looking for things that are across waves, where you can also do the single wave version, you need the right wave specifications in your analysis. In terms of all waves weight, we construct those weights to give you statistically valid estimates for things that happened over time. This dataset will have a modestly smaller sample size. The single wave weights are really created so that you have statistically valid representation for any given cross-section. Once you put them together across waves, single wave weights normally should be fine. This is true if your analysis is indeed purely cross-sectional. However, if you are looking for patterns across waves, you will lose observations in which you missed a wave. In that case, the fact that each wave is representative across-sectionally is not sufficient for joint representativeness across wave. The bottom line is, if you are going to be stacking waves and single wave weights for analysis to get a bigger sample size, then we recommend that you then repeat the same analysis using the all waves dataset to make sure that results at least stay comparable so that there's nothing strange or artifact in your analysis because of the selection of the respondents over time. It's similar with what we did here, and we do see some significance changes, even though the size or magnitude are similar. So this example shows you that you can stack the single wave weights, and that would be appropriate in this particular case. But by having evaluated the model both ways, we have a better handle on that.
We are now moving to the latent class example. So far, all the examples we provided include outcomes and predictors that are observed. Now we are entering to the latent world, where the outcome and some of the predictors are not actually observed. You need to use observed variables to indicate the existence of them. The example we are using is called latent class analysis, which we will do in M-plus. But we will show you that all those basic steps are exactly the same with what you've seen in the SAS examples. Some brief background about this latent class analysis framework. This technique is used to group individuals with similar characteristics. The indicators can be continuous and/or categorical. Sometimes, if the indicators are all continuous, people call it latent profile analysis, if you are familiar with that term. In this webinar, we will show you how to incorporate survey weights and replicate weights to generalize our findings to the target population. Therefore, we need some additional components to the standard analysis. Since we have to loop through all the replicate weights, we are going to use a loop function. The R package, M-plus automation, will provide some convenient functions to help us do this very efficiently. The research question we selected for this example is first, among adults who are 18 to 24 years old, do they have distinct response patterns to tobacco dependence? Second, how do those dependence groups differ on gum health status after controlling for demographic characteristics? All the variables we are choosing for this particular example come from the Wave1 puff file, including the adult weights. We will subset to 18 to 24 years old adults and identify possible tobacco dependence groups. We would like to explore the possible connection between the tobacco dependence groups with a distal outcome. That is, whether people ever had treatments for their gum disease. We want to control the effects coming from demographic characteristics such as sex, race, ethnicity.
Now we will explain all the variables going to be used in this example. We selected 16 variables that came from the tobacco dependence section in the interview questionnaire. All but one variable was in Dr. Strom's study that was utilized in the first two examples in Part 1 of this webinar. Recall that all the questions are on a Likert scale, asking for degree of agreement to a specific statement. For simplicity, we dichotomized those response categories into two. We recode values 3 to 5 into one group, which means agree with those statements and giving a value of 1, and values 1 and 2 means disagree, and we're giving a value of 0. Based on their response pattern, we would like to identify the latent classes, but we also want to explore its relationship with the distal outcome, treatment for gum disease. The distal outcome is also from an interview question, RO1_AX0130, which has values 1 equals yes and 2 equals no. But we recode value 2 to 0 in this example for easy interpretation. When we explore the relationship, we would like to control for the possible effects coming from the demographic characteristics. The two demographic variables we selected are sex and race ethnicity. Respondents are asked about their race and their ethnicity separately at the first wave they participated in the past study. Response options for each are combined into non-Hispanic white, non-Hispanic black, non-Hispanic other race, including multiracial, and Hispanic. This part of model is usually called auxiliary regression model. In addition, we also would like to see whether those demographic characteristics would impact people's class membership in those latent classes. When we explore the relationship between latent classes and demographic characteristics, it's essentially a multinomial logistic regression model. Response options for sex are 1 male and 2 female. Again, we recode value 2 to 0 in sex. Since M-plus can handle nominal variables, we have to create 3 dummy variables to represent the 4 race ethnicity groups. 1 for non-Hispanic white, 2 for non-Hispanic black, 3 for non-Hispanic other, and 4 for Hispanic. For race ethnicity, we use non-Hispanic other group as a reference group. Similarly, for sex, we used female. So the asteroid here is the reference group. We would like to make inferences to the whole population, so we will need to apply sample weights. We will use the full sample weights to get the class membership estimation, as well as the point estimates for the regression models. In order to get the correct stand errors, we will need to repeat the step through the 100 replicate weights. We will use the modified BCH methods implemented in M-plus. The BCH method is named after the three authors, Bulk, Crum, and Hagenars in 2004. This method is later modified by Vermont in 2010 and Beck et al. In 2013. There are two versions of BCH method. M-plus calls the first version automatic version, which is suitable for evaluating the mean of a continuous distal outcome across those latent classes. Then another version is the manual version, which is suitable to estimate the effect of a latent class variable on an auxiliary model. That is exactly the kind of model we want to explore. In this example, therefore, we are taking the manual approach. For more details about the BCH methods and how it's implemented in M-plus, I suggest you refer to Asparuhov's and Mutim's web notes from M-plus website, which you can also find in the presentation references. You will see that it was revised recently. When this example code was created, it used in the 2020 version. So the model setup is slightly different from what you will see in the next few slides. To do the manual version of the BCH method, it actually requires two separate rounds. The first step is to estimate the latent class measurements model with full sample weights. We need to output the BCH weights, which reflects the measurement error of latent class variable. Please note that we are not saving the latent class membership from the output and then treat it as an observed variable in the analysis later. That is not what the BCH is doing. Actually, it will re-evaluate the class membership with the presence of distal outcome as well as those possible covariates in the model. That is what we will do in step 2. In step 2, you will see that we will use the BCH weights outputted from step 1, get the point estimates using the full sample weights, and loop through the replicate weights to get the correct stand errors for the regression coefficients. Now we will see how the model will be set up in M-plus. This is the M-plus syntax for step 1. Recall that in step 1, we need to identify the latent classes. This is a mixture model problem. The very first step is to determine the number of latent classes. That's why I highlighted the classes statement and the N in red, because that's a parameter that needs to be manipulated. This means we will run through a set of candidate values for the number of latent classes with the same setup. The M-plus syntax can be divided into small sections. From their title, I hope those sections are self-explanatory. You will give a name or title for the whole program. The data section specifies the input file for the analysis, and the variable section gives the variable names in the input file and what to use for analysis. For this particular example, we specify the auxiliary variables that include the demographic characteristics as well as the distal outcome. Hispanic, non-Hispanic Black, and non-Hispanic White are the three dummy variables for the race ethnicity groups. By doing this, they will be carried over to the output file. The indicators for latent classes are all categorical. Any missing values are recoded to 999. M-plus doesn't allow blank or dot for missing values. You have to replace missing values with a special value and specify it in the missing statement. We will use full sample weights for the first step. Classes statements is where we specify the number of latent classes we want to keep. The type of analysis we use is a mixture model, and we will save the output to a file called lca_example with number of classes and full weights. Here, we also request the BCH weights to be saved in the output file. Those BCH weights will later be used in step 2. To determine the number of latent classes, there are several ways of doing that. The standard way is to look at the model fit index. Since we have weights in our analysis, the recommendation from M-plus is to use BIC. That's the Bayes' information criterion, which accounts for a complex sample design in the calculation. For those information criteria, a smaller value means a better model fit. We are looking for a turning point, which is the smallest value. Based on the output here, it seems BIC is the smallest when we keep 7 latent classes. For illustration purpose, we will only present results for a model with 3 classes. Another way to determine latent classes is the likelihood-based test. However, those tests may not function as well when we have the sample weights added to the analysis. That is why we will follow the recommendation to use the BIC. Here are selected outputs for 3 classes. When we only maintain 3 latent classes, the first part to look at is the final class counts based on the posterior class probabilities. As you can see here, among the 3 latent classes, more than half of the sample fall into class 3 with 2,831, and class 1 and class 2 take almost an equal number of respondents. Class 1 has slightly more respondents with 1,243 compared to class 2 with 1,099. M-plus also presents the selection probabilities in the class indicators within each of the identified latent classes. I reorganized those outputs into a table so you can easily tell how those classes are different from each other. Here is the list of indicators we used. I also include the descriptions of those questions. The numbers in the right 3 columns are selection probabilities. You can consider them as how likely a respondent will endorse each of those statements. Or you can interpret them as the proportion of people within a latent class agree to the statements. For example, the first indicator is about whether people feel they reach out for tobacco products without thinking about it. 92% of the respondents said yes in class 2. In contrast, only 8% of the respondents from class 3 agree with this statement. Since all those questions are selected from the tobacco dependence section, they indicate a degree of dependence or addiction to tobacco. If you go through them, you can see that class 2 always have the highest probability to endorse the statements. We would consider class 2 to have severe tobacco dependence. Class 3, in contrary, always have the lowest probabilities, so their dependence is low. And class 1 is kind of in between. Therefore, it's possible to label the latent classes based on their selection probabilities or response patterns on those indicators. Where class 1 is some degree of dependence, class 2 is severe dependence, and class 3 is minimum dependence. This is one possible way of labeling these classes, but definitely you can use other labels for those classes. Once we have the number of classes determined, that's when you move to step 2, where we will have the presence of the distal outcome and the covariates in our model. The structure of the M-plus syntax is very similar with step 1, but with additional components. The input file is actually the output file from step 1. That means we are taking the 3 classes solution with full sample weights. In this input file, we have the original indicators for latent classes and all those auxiliary variables. W1 to W3s are new. They are the BCH weights outputted from step 1. We still have our full sample weights. PID is the aide variable to keep in the output file. This is because we are going to use PID when merging the variables onto the input file when we do the replicate weights. In use VAR, we have those auxiliary variables, distal outcome, as well as the BCH weights. You don't see the 16 indicators for the latent classes because they are actually controlled by those 3 BCH weights here. Those weights are used as the training data. In this syntax, you will see that we still use the full sample weights in addition to the BCH weights. And we request 3-class solution where we are running another mixture model. However, we will need to specify the 2 regression models in the model section. You can see here the latent class C and the distal outcome, the gun treatment, are regressed on the demographic variables. As I explained previously, the first row is basically a multinomial logistic regression. We would like to see how those latent classes will differ in terms of those demographic characteristics. And the second row and the following sections with each of those 3 classes are for the auxiliary regression. The setup here is to explore the relationship between the latent class assignment and the distal outcome while controlling for the demographic variables. Lastly, in the output, we request outputs the final estimates from this model. Those values will be later used as starting values for the replicate weights. Let's look at the results. You can see that the final class counts actually change a little bit with less than the decimal differences of 1/100th. This is because we never save the latent class membership as an actual variable in the analysis. It's part of the modeling process. However, because we use W1 to W3, the BCH weights, there is only a very small portion of people who switch classes in the second step. That is exactly what we want. For the auxiliary regression model, we get the estimates, the regression coefficients, for each of the latent classes. You can probably think of this as a multi-group analysis. The regression model are conditional on the latent class we identified. For the multinomial logistic regression part, we also have estimates of demographic characteristics. We have one latent class serve as a reference group. Here, class 3 is the reference group. The results on the right under categorical latent variables basically shows the regression coefficients for the multinomial logistic regression model. However, because we use full sample weights, we are only interested in the point estimates and its class membership assignment. Now, we need to repeat the whole process for each of the replicate weights. But to do that, it requires additional steps. The whole process will be much more complicated than what we did in SAS examples. If we want to do this with replicate weights, we need to do a M-plus bench run in R. The very first step is to prepare the input file. As I mentioned before, we need to merge those BCH weights outputted from the full sample weights onto the file with all the replicate weights. We will also use the final estimates from the full sample run as starting values for replicate weights. By doing that, we can avoid people switching classes. This will help later by making merging the coefficients much easier. Also, sometimes we will encounter non-convergence problem for some replicates. Using starting values, we can reduce the chance of non-convergence. Since we have to run through all the replicate weights, we can prepare an M-plus syntax template that we can use to generate a set of syntax for each of the replicate weights. We call this template LCA_example_rep.wgt.txt. It's saved as a txt file. the very first portion of the syntax is to tell the program that there is one parameter that I need to manipulate throughout the template. This iterator is called rep, and it will take sequential number from 1 to 100. All the outputs coming from this template will have similar naming convention. That is, LCA underbar example underbar SMP rep bracket bracket rep bracket dot inp. Those output files are the M-plus syntax for each of the replicate weights. The outputted syntax will be saved in the folder called replicate weights. The rest of the template is very similar with what you've seen in step 2 for the full sample weights. We still have a title, but here we replace the full sample weights with the replicate weights under variable. The input file is the one with all the BCH weights and the replicate weights. The weight variable is now one of the replicate weights. Although we still run the mixture model, but we don't need to generate starting values. Instead, we will use the final estimates from the final full sample weights for those replicate weights. Here is where the R package comes in. The M-plus automation package offers very nice functions to generate the syntax using a template. We use the function called create models, where we just specify the location of the template. It will generate a list of syntax as we just specified. Within each syntax, you will have similar codes for one specific replicate weight. For example, if the title includes replicate weight 1, the variable weight would be something like repw1. The output directory now stores all the outputted syntax. The next step is to run all 100 M-plus syntax. The run models function from M-plus automation will execute all M-plus syntax in the designated folder. That is exactly what we want M-plus to do. Now, we have the outputs from the 100 replicates weights run. The next step is very similar to the SAS macro. That is, we collect the point estimates and calculate the stand arrows and the significance level. This part of code is to extract the estimates from 100 replicate runs. The read models function from M-plus automation will read each of the M-plus outputs into R. We further specify that we want to keep the parameters table in the output file. The 4 columns we want to keep are latent class, param header, param, and the actual estimates. We also rename the estimates from each replicate to have the prefix est underbar with a replicate number. This is to prepare merging the results with the other estimates. The collection of this part will be a list with 100 elements. The reduce command is to merge all those files into one single data frame. This is the output from the code just presented to you. The top part of the table contains the estimates for the auxiliary regression models for the distal outcome under each latent class. These estimates in column headers start with that est underbar prefix we assigned before. These are the regression coefficients of the demographic variables, intercept, and residual variance. The bottom part of the latent class column is the multinomial logistic regression, where we have the coefficients of the demographics variables and intercept of the latent classes. We then merge this file with the point estimates from the full sample weights. We use full underbar join statement to merge those two datasets together. In the mutate underbar add statement, we calculate the squared of the difference between the point estimates and the estimates from each of the replicates. And within the mutate statement, we calculate the variance by taking the sum of the squared difference, then stand arrow, t-test, and p-values. These are the exact same steps as we did in SAS macro. For presentation purpose, we format the numbers by keeping 3 decimal places in the output file. I organized the outputs with adjusted stand arrows from replicate weights into this table. There are 2 sections. The first part is for the auxiliary regression model with the distal outcome for each latent class. We can evaluate how those classes differ on the distal outcome after controlling for the demographic characteristics. The interpretation will be very similar to regular regression models. The intercept is basically the mean value when all the predictors are 0 in the model. Among the 3 latent classes, Class 2 has, on average, the largest intercept, and recall that this group is the severe dependence group. This means people who have the greatest dependence to tobacco have the highest probability to have a treatment for their gum disease. Class 1, the groups with some degree of dependence, have the lowest probability to get treatment. We can also interpret the effect of demographic characteristics. Here, the positive value means a higher probability to treat gum disease than the reference group. Significant sex difference is only observed in Class 3, the minimal dependence group. Males are less likely than females in Class 3 to treat their gum disease at negative 3.170, which is nearly double the value of Class 2 and 6 times the value of Class 1. In terms of race ethnicity, the 3 latent classes showed quite different patterns. Still in Class 3, non-Hispanic white is the only group that has significantly lower probability to treat gum disease compared to the non-Hispanic other group. In Class 1, people with some degree of dependence, the significant group differences at just over a value of 2 is found in Hispanic and non-Hispanic Black compared with the reference group. But no significant group differences is observed in Class 2, the severe dependence group. The second part is for the multinomial logist regression. Here, Class 3, minimal dependence group, is used as a reference class. But in M-plus, it actually provides the parameter estimates and log odds when a different latent classes is used as reference. I only presented the parameter coefficients, but we can also calculate the odds ratios. A positive coefficient means a higher probability than the reference group. Recall that Class 3 is the largest group. The negative intercept for Class 1 and Class 2 means people are less likely to fall into those 2 classes than to Class 3 after controlling for the demographic characteristics. We can apply similar interpretation to the coefficients of the covariates. For example, male is significant in Class 1 and its value is positive. This means, compared to the minimal dependence group, males are more likely to be classified into the group with some degree of dependence than females. Here is a quick summary of the findings from the latent class analysis. In our auxiliary regression model, we identified 3 tobacco dependence classes. When exploring its relationship with the distal outcome, we found that for severe dependence group, we don't really see group differences in terms of sex and race ethnicity. For some dependence group, Hispanic and non-Hispanic Black are more likely to treat their gum disease than the non-Hispanic other group. For people with minimal dependence, males are less likely to treat their gum disease than females, and non-Hispanic whites are less likely to treat than the non-Hispanic other group. In terms of the people's likelihood to be in one of those latent classes, if we are using the minimal dependence class as a reference group, we can see that for severe dependence, there's a significant race ethnicity difference. For the some dependence group, we observe that males are more likely to have some degree of dependence than females, and the Hispanic group has the lowest likelihood to be in the some dependence group in this example. Some final recommendations. M-plus is a flexible software which can handle many types of models. You can easily extend the process described in this webinar to other types of longitudinal latent variable analysis, such as latent transition model, where the people's status or class membership at certain time points is conditional on the status in the previous time point. You can also apply a similar analysis process for growth mixture model, where we group people depending on their growth trajectory. All you need to do is to modify the model setup in M-plus. The basic steps are exactly what we just presented if you are using the BCEH methods we presented here. As a final note, SAS offers proc LCA function that can also analyze the latent class model. However, we have not evaluated how they will handle the weights in the analysis. If it's possible to apply the weights to proc LCA, you can definitely go back to the SAS macro we introduced in Part 1 to do the replicates. But as to latent class membership, remember that you will only rely on the full sample weights, which are just the point estimates. For that part, we don't need the replicates weights.
Now you have seen all the examples, we come to the last section of this webinar. This is an abbreviated version of the slide we started with. The PATH study is nationally representative of the US population, but it's collected using a complex sampling design, which means you should use weights and replicate weights when you analyze it. Therefore, you have to use survey-appropriate methods. If you do that, you end up with results that are statistically representative for the US population. But what does that really mean? I want to spend a few moments interpreting that statement. What are you really doing when you are fitting a model using survey weights? What you're estimating is something as if you had observed the whole population of the US, as if you had fitted that same model to the US population. You would obtain a set of coefficients for the US population with the sample. Because of that, intuitively, if you make 95% confident interval of the value you get from the sample, you can make a statement that says, I'm 95% sure that the value that I would have obtained if I had fitted to the whole population falls into the interval. That is a stronger statement than what you can typically make if you have a convenience dataset. And you can only make that statement if you use the survey weights and the replicates. You use the survey weights to get the point estimates and the replicates to construct 95% confidence interval. But if you go through all that trouble, then this is a statement you can make. The US population for that same model would be in the interval. If you don't use the weights on those data, you can still fit models and get intervals, but those intervals are only with respect to the specific model that you had fitted to your sample dataset. If you do this to the extent that your sample dataset doesn't look like the US population, you can't make that same statement you could conclude above. When you get your coefficients and their significance level, you realize that you really are allowed to extrapolate from your sample to the US population. In closing, you have to use survey-appropriate methods if you want to be able to make statements about representativeness. The easiest way to take the survey design into account is to have the software handle it, to the extent that you have a procedure that's already programmed that will take your full sample weight and your replicate weights and give you the results. But for many types of analyses, you don't have that. For those methods we described, analysts can use the manual method or macro that implements the weights and calculates the variances. We showed the manual method here for a set of very specific models, but this holds true in general. If you have an analysis, as long as your procedure can handle weights, you can use this approach that we did here to conduct your analysis and to obtain your significance levels. Here are the references for the examples used in this part. And that's it. Thank you very much for taking this webinar with us. If there are questions, you can write to the pathdataUserQuestion@westat.com email account. This presentation is supported with federal funds from the National Institute on Drug Abuse, NIDA, National Institutes of Health, NIH, and the Center for Tobacco Products, CTP, Food and Drug Administration, FDA, Department of Health and Human Services, under contract to Westat, contract numbers HHSN 271-201-100027C and HHSN 271-201-6000001C, and through an interagency agreement between NIH NIDA and FDA CTP.